Hi, everyone. Let me go get my slide and then share the screen. Okay, we're going to continue the subject of file system. We're focusing on a very basic file system issue is logically that a file is a sequence of bytes. And how do we actually place them in the hard disk where the physical locality of the block to represent those files, to store those files, might be in a different order, but we still need to preserve the original order. And also we talk about, very importantly, how do we efficiently access the file in a random access fashion. Okay. So that's the issue that we left off on Tuesday. So today the focus is to introduce a basic data structure called inode. Depending on how fast I can move, maybe I will talk about inode, then talk about UFS, which is directory, depending on how fast we can get there. So just to show you the picture where we are, that this is the picture I showed you last time. It's a kernel. And in next couple lecture, I try to go through the whole red box. That is from the hardware, the hard disk, the blocks, all the way to the vNode area. I mean, there's one thing you need to learn about inode, but the other thing which you should also learn is what is a vNode? And what's the difference and what's their role and how do they provide different kind of abstraction in the information that we need to organize by the operating system kernel. Okay, so let's actually first talk about inode. So if you ask me what is the inode, what it of course is helping us to mapping the logical file into the physical disk block. It's really, if you ask me, I would say it's just a 13 pointer or 15 pointer. Well, usually it's in a FreeBSD operating system, it's 15. Those are 15 pointer. Here is inode on the left side, this 15 pointer. So there are 4 different category of pointer. I represent in color here, the sky blue, and then the yellow, the pink, and then the green. So the sky blue pointer, those 12 pointer, by the way, if you look at different version of file system, the number of the sky blue pointer might be somewhat different. Some of them has 12, some of them may be less, some of them may be a little bit more. And those 12 pointer is called direct pointer, direct block. We sometimes call it direct block because those blocks are being directly pointing at this 12 pointer. So essentially, this 12 pointer represent the first 12 data block about the file will represent. Okay, so this 15 pointer here, the first part, 12, is what we call direct pointer or direct blocks, or representing direct block. Okay, so if you think about your block, say each block is 4K byte, then if you have a file which is less than 48K, because you have a 12, each is a 4K, so you can actually point to 12 different disk blocks totally. If your file size is less than 48K, then essentially this 12 pointer will be sufficient for me to pointing to the blocks that I need. Okay, so for small file size, I would just use the blue. That's fine. Okay, obviously that the file size is going to be much bigger. A lot of, especially right now, today, the file size tends to be grow bigger and bigger. So if you have bigger than 48K byte as a file size, then you're going to use the yellow block. Yellow is called single indirection. Single indirection. So single indirection is that means that this pointer is not directly pointing to the disk block related to the file, but it's actually pointing to something we call it directory, a pointer block. So the pointer block basically contains a bunch of pointer. So think about the disk block here, that assuming this is a 4K, remember we say assumption in this example that one of the disk block is a 4K byte. So if it's a 4K bytes, if you actually have a pointer size, means the address, let's assume it's a 64-bit architecture. So 64-bit architecture, each of the address, okay, by the way, each of the address should be 64-bit. That's 8 byte. So if you have 4K byte with each pointer is 8 byte, then this block, you're going to have a 512 pointer because it's all power of 2, right? 4K byte is 2 to the 12. And each of the pointers is 2 to the 3, 8 byte. So 2 to the 12 divided by 2 to the 3 is 2 to the 9. That's 512 byte. So essentially, this one, instead of like a blue directly pointing to the disk block, the yellow is actually first point to another block, but this block is everything is pointer, is a 512 of them. And this basically represents the 13th block all the way to 525th block about this file. So essentially have this first 12 block plus this 512 block, that's the file size that the single indirection can handle. Okay, so if you have a file size which is sufficient for to be 525 disk block. 524 disk block, each is 4K, then use both direct and single indirection, you will be able to represent the file. Okay, so let's just forget about purple and the green, because if you understand yellow, you understand purple and green as well. Okay, so let's just worry about the blue and yellow. So right now, what I'm showing in front of us is essentially 524 pointer, basically 12 direct block plus another 512 pointer. They all handle pointer to this, the right-hand side, which represent your hard disk, and then it can point to about 524 of them. And that's logically belong to the same file, but the order of this logical file is determined by the order of the pointer. First is a blue, and then it's a yellow. Okay, so that's the first order representation. We use the direct block plus the pointer block, and then we can actually represent a file looks like this. So before we move on to the pink and the green, that we actually provide some kind of direct access to the block. Because if you want to access a particular position in the file, so usually if you use a system call called fseek, and fseek, you basically provide the offset from the beginning of the file about where you want to access in the whole logical sequence. And essentially you divide that by the block size, 4K. And then you will be able to know which block will contain the position of the file that you try to access. And therefore, what you need to do is, typically, this is the way to do, is that first you want to access a file. When you open the file, you're actually going to open this inode. This inode data structure, later I will show you itself, is about 256 bytes. And you want to get the inode, which this inode will be cached from the hard disk to the memory. So you're going to have that one disk access, and you bring this inode into the memory. And then what you're going to do, you realize that, okay, you need to access the single indirection block, which is the yellow one. And then what you will do is you actually going to have a second memory, a second disk transfer for that yellow pointer block, move it to the memory. So essentially you move two blocks. One block contains the inodes on the left. The second block you actually bring in from the disk about the single indirection block. And to bring in this two blocks in your memory, then the subsequent access to the disk block, you have all the information because you already have all this 524 pointer in front of you. When you do fseek, when you want to fread certain portion of the file, you actually will use the position of the pointer you try to access, and then you try to determine what is the block that's actually represent that. Then you're going to bring in only this block that's actually you're interested. So this model is a nice trade-off. You only need a couple indirect block into your memory or cache. Then you can actually access pretty much everything everywhere in a pretty large file that represent by this data structure called inode. Okay, so just very simple extension. If you understand the concept of a single indirection block, then what's double indirection? So the pink is called double indirection, and the green is called triple indirection, because sometimes 524 blocks are not going to be enough to contain some of the file. And so you need double indirection. So double indirection means that this pink pointer, the 14th pointer, is going to pointing to a pointer block. But this pointer block also have a 512 pointer. And this 512 pointer is not also directly pointing to the data block. Instead, they are actually pointing to the 512, what we call the second indirection block. So this is the first indirection. This is a second indirection block. And over here, you can see that you have 512 times 512. So you have a 2 to the 18 blocks, 2 to the 9 plus 2 to the 9. So over here, you actually, with double indirection, you're going to have 2 to the 18th pointer and times the file size that this is going to be able to handle 2 megabyte. By the way, the file size of 2 megabyte. Right. So that's double indirection, but 2 megabyte is not a lot, right? So that's why you need triple indirection. You have the 15th pointer in the inode pointing the single indirection, the first pointer 512 to do another 512, and then to another 512. So this third level, you're going to have 2 to the 9 times 2 to the 9 to the 2 to the 9. You can address to 2 to the 27 blocks. If each block is 10K, you can calculate that you can actually address a pretty big file with a triple indirection. Okay, so if you ask me now, what is inode? Inode is those 15 pointer we're talking about. And those 15 pointer, the last three represent is pointing to what we call indirection block, which allow you to access the file with a few disk block that you need to grab in to represent the as part of inode. So the few block you need to bring in, not just the inode block itself, but also block the proper indirection block. For example, if you want to look at, like I mentioned, I like to watch the last 5 minutes of the movie. So apparently that must be addressed by triple indirection block. So I calculate the offset about the location I want to watch. So likely you're going to first bring in the first indirection block from the triple indirection block, this one. And then you might need to bring another one, second one, and then the third one. And then I'll be able to do that. So essentially, this is bringing 1 block, 2 block, 3 block, 4 block. Then essentially, I can access anything I want, regardless how big the file is, assuming this is actually be able to handle a really, really big file. Okay, so that is conceptually how a inode is being designed to handle this kind of environment. It's a nice trade-off between representing every information in power 2, and everything can be stored in the block of power 2, and yet it provides a reasonable way of doing logarithm speed to represent any size of file in random access mode. Okay. Okay, I'm going to pause here for a moment. I saw there was some chat. I need to take a look. Okay, all right. So let me. Okay, so Green Sam, you're asking about the numbers, right? And then, yeah, I probably should do that in the site. No problem, I can do it now. Hold on, let me escape. Wait a minute, why can I escape this? Ah, okay. I hope I'm still, oh, wait a minute, I need to share my screen. Okay, I'm going to put it down this way. So this is a 15 pointer. And we're assuming each pointer is 8 byte or 64-bit architecture. All right, so that's the first order bit. Let me actually make the font size a little bit smaller so I can write more information. And also we're assuming each disk block is 4K byte. That's actually 2 to the 12. All right, so that's the basic number we're operating. Okay, so now we're actually looking at this. Let me make a copy of this here. So because each of the disk block is 4K byte. So I use 4K, which is 2 to the 12, divided by the pointer size is 2 to the 3. This becomes 2 to the 9, which is 512. Okay, let me actually put a color here so we can nicely see it. Okay, yeah. So this yellow box here, I want to discuss a little bit. Let me actually make it a little bit bigger. Here. Okay, this is the assumption about what we have, right? And the thing is that this block, by the way, indirection block is also a disk block, but this disk block does not contain the data. It's only contain the pointer to the data block or in the double and triple indirection, they could be pointing to other pointer block. But anyway, in this kind of block, everything is power 2. And each block, because the size is 4K, so the size is 2 to the 12 by. And then I actually have 64-bit architecture, which is 8 by. So it's a 2 to the 12 divided by 2 to the 3, which is basically 2 to the 9, which is representing is 512 pointer. So essentially, what I'm saying is that each of the pointer block, they contain 512 pointer. By the way, just be careful. This is a very system configuration dependent. Let me just give you an example. The calculation will be totally different today. Older architecture, if it's a 32-bit architecture, 32-bit architecture is going to be, the address is only 4 byte. And therefore, this is 2 to the 2 instead of 2 to the 3. And in an earlier system, typically, I don't know when they start to do larger this block, but it used to be this block is 1K byte. If it's 1K byte, this is 2 to the 10. So it's a 2 to the 10 divided by 2 to the 2, which means that each of the pointer block only actually contain 256 pointer. So that's actually because the larger the disk block and the larger the size is actually give you more addressability about how much you can actually address. Okay. Does that help you understand the number? Let me see. Let me actually get to the end. Could you clarify? Okay. Okay, so Nishan, you asked me about the trade-off, have multiple indirection pointer. Here is a trade-off, is obviously when you have a third triple indirection, to access the disk block is a bit slower because you need to first retrieve 3 disk block before you can access to any block that's actually being pointing by the green section. But this is essentially a way to very quickly to use a less amount of hard disk to actually store the pointer. If you don't have triple indirection, just example, if you don't have triple indirection, the inode will be a lot bigger because see, this is a file. I'm actually representing all the inode with only 15 pointer. But think about, I can potentially just remove all the indirection block. If you don't have single, double, triple indirection block, then I'm actually going to have an inode or equivalent. It's going to have a huge amount of pointer, like this amount of pointer, this level, this pointer, and the third level pointer all has to somewhat squeeze in to the inode itself. So inode is the beginning of your accessing your file. So this essentially is a trade-off saying that, well, I have an inode, which I want to keep it really small. In fact, the design today is about 256 bytes. That's the UFS2 inode. If it's UFS1 inode, it's actually only 128 bytes. So just let you know what's the difference between UFS2 and UFS1. UFS2 is 64-bit architecture. That's why the pointer is bigger, so you need 256 bytes. UFS1, at that time, is a 32-bit architecture, so the pointer size is small, so that's why inode becomes smaller. So the design is 128 bytes. We'll see the code in a moment. Okay, so essentially, it's an engineering design. It doesn't say it's an optimal way of designing thing, but it's a nice design to have you represent the initial of the file with a small, relatively small memory footprint for access a file. By the way, there was one property I should mention about inode design is that it's actually pretty efficient to handle if most of your file are small. If you have a lot of small file, because small file, I mean, if you think about today, you want to think about a typical company, they have a large file like a video, but they also have a lot of small file like your email, each of the message. And with this small file, it's actually very nice to use this inode because it's small and they can handle a large amount of that information. Okay. Oh, the question is, where does the interaction block lies? The indirection block, they're also in the hard disk. Okay, they're both in the hard disk, which I will actually show you the memory map on the hard disk, so you will know precisely where those files. Well, you can think about, you have an inode block, you have an indirection block, you have a data block, you have a directory block. In fact, when you look at a file system, essentially you have 5 different kind of block. The first one is called super block, and you have an inode block, you have the indirection block or pointer block, and then you have what we call directory block, and then you have what you call data block. So essentially, that's all kind of block. They all putting in a hard disk partition for a file system. Okay. Okay.
Professor, I had a question.
Sure, go ahead.
If the file is too large, does that mean that the direct blocks are empty?
No, the direct block will not be empty. So you always used up all the pointer in the direct block before you start use first indirection. And you used up all the indirection before you start to use double indirection. And after you filled up, you used up all the pointer. So essentially, each of the pointer here, they also represent the logical sequence. The first block in your file, remember, file has a sequence about all the bytes. So the first block is always on the first direct block. This is the second block, third block, fourth block, and so on and so on. So essentially, the last few block about your file, if it's a triple indirection, is always somewhere here. Does that clarify your question?
Yeah.
Okay.
Thanks.
You're welcome. Let me actually. Zen, yes. In fact, it was my favorite final question about, given all the parameter, that the number I put in here, you can actually calculate what is the biggest file that you can actually represent in a file system. I mean, every single file. So for example, the most commonly used file system, it used to be, probably still is, it's FAT32. I mean, I don't know if you heard about FAT32, is all the Windows systems started with FAT32, then they have NTFS, and then they have an ext-FAT. So with FAT32, the limitation of the file size is 4 GB. So that's why if you actually, for example, you configure a USB disk with FAT32, which means that the largest single file that you can put it in is 4 GB. I mean, regardless how big your USB drive is. So if your USB drive has, like in my typical setup is about 16 GB. A hard drive is 16 GB, but if you configure that with FAT32, the single file you can put it there, the largest is 4 GB. It doesn't matter. And in order for you to break that limit, you actually have to either configure your device to be, say, ext-FAT, which is ext-FAT, then you can actually break that limit, or you use NTFS. You don't constrain. Okay. All right, I'm going to stop for a moment and ask, do you have any other question about the basic introduction about inode? Any other question? Okay, let me go back to Right, next topic. Okay, so what we did is that the requirement of file system, you actually see that there is a performance issue, efficiency issue. And gradually, I'm actually going to talk about this data structure design, also have some recovery or robustness issue related to the design, and also have some kind of extensibility that you can do a lot of things. But now I'm actually going to show you a piece of code about this is the source code for inode, the declaration about as a structure. So you can see that this is actually UFS2. Why do I have security concern? Hyperlink, no. Did you see the error message? Okay. Okay. Wait a minute. Hello, can you hear me? Are we still online?
Professor, we can't see your screen.
Oh, okay. That's because somehow Zoom posts some error message. Let me just share this. Thank you for letting me know. Yeah, now you can see my screen, right? Oh, not this one. This is my different lecture. Must be this one. Okay. Okay, so this is a piece of code that's actually define what is UFS2 inode, which is a 64-bit architecture. So let's first look at the structure of inode, because this exactly data structure is how you're going to store an inode on a hard disk. Remember, inode is actually need to be persistent. When you turn off the machine, the inode is still there. So let's actually first count how many bytes of this inode. So if you look at this is actually very nice. They have the number shows here. So this, okay, I would say yes this time. Fine, that's fine. Okay. So so this is actually showed the beginning of the file. So basically, why is keep try to access this? Interesting. Okay, I must have some hyperlink that's actually keep probing on the source code. Okay, so this is the first byte, which is byte 0. That the first. Let me actually check why. Is there any way I can just ask PowerPoint to don't worry about this and just let me, any tips you can share? That's actually very inconvenient. I have to keep pressing this. Okay, so this is the inode structure that this is the byte, the first byte is actually the first. Ooh. You know what? I'm actually going to do this. Can you still see my screen? I think maybe I don't do display. I just do this. It might be okay.
Yeah.
Okay, you can still see the screen. Okay, this is, I need to figure out how to get rid of that. All right, so this is the first byte, which is byte 0. And this is the byte 232. Okay, so this is the byte 232. And this data structure has an array of 3 elements. Each element is integer 64, so it means 8 byte. 8 byte times 3 is 24 byte. And if you add 232 plus 24 is what? 256, right? So which means that the whole data structure is designed to be exactly 256. So let's actually go back to our previous discussion. If this is I know block, right? So by the way, one of the block is I know block, and each block is 4K is 2 to the 12, and then one of the I know is actually 256 byte, which is 2 to the 8. Now you can see that how many I know that you can have in one block is 16, 2 to the 4. Okay, so the thing is that now you actually see that the design of our system is all power of 2. So we have a disk block, which is 4K byte. Each I know is 2 to the 8, which is 256 byte. So it means that each of the I know block can actually host the I know for 16 files. Okay, so when we talk about I know, it's a fixed size 256. So first, let's clear that. So you understand that that's the design. Again, it's power of 2. Okay, so now the second question I want you to actually figure out. I want you to figure out where is those 15 pointer. I want you to look at the code in front of you, because remember I said there are 15 pointer. Where do you think are the 15 pointer?
Line 146.
Yes. Actually 145 to 147. Let me actually go over here. Okay, so think about, oh yeah, sorry, you're right, 46 and 47 actually. So 47 is called direct block and 47 is called indirect block. All right, can someone tell me what do you think? This is ND-ADDR and NI-ADDR. Those are the macro being defined somewhere else. Can someone tell me, you don't need to do Google, but just look at the information in front of you. What do you think the number ND-ADDR? What's the number? Let me actually say, what do you think is the number of ND-ADDR is equal to what? And also, what's the number of NI-ADDR?
15
What are
and
those
3.
two numbers?
NDADDR is probably 12.
Okay, how do you actually figure out it's 12?
Because the offset is 112, and the next offset is 208. So that's 96 bytes for the DI underscore DB array divided by supposedly 64 bits. So that's 8 bytes that will come to 12.
Excellent, excellent. That's exactly how you can figure out without even looking at the code where they define NDADDR. So exactly, so it's a nice, they actually put all this by sequence in their code for UFS2. So you can see that's, you're exactly right. NDADDR is actually 12. And then NIADDR, the same way you can actually derive, you take a 232 minus 208, that's 24. 24 divided by 8 is 3. So those 15 pointer are basically contained exactly here. Okay. All right. So that's UFS 2. I know. Any question? Okay. So now I'm going to move to another data structure. I will actually talk about what's DIN links later, because that represents something we call hard link. It's different from symbolic link. We'll talk about how do we use that information, DIN link, later. But right now, I'm actually going to talk about these two blue things here. One is called DI size. One is called DI blocks. So can someone tell me what do you think DI size represent? What DI blocks represent?
DI size is probably the actual size of the file versus how many blocks it occupies. So there can be few blocks that are partially occupied.
Are you talking about DI size or DI blocks?
DI size and blocks. So DI size is the actual file size. DI blocks is the number of blocks that the file occupies. They can be different in case a block is partially filled.
Okay. So I want to ask you a question though. Let me actually, I know what I want to do. I want to use this one. So I have a one called DI size, one called DI block, right? And so as we say DI size, assuming the size is power 2, okay? Assuming it's power 2, that make everything easier. And then DI block is number of block that we need to represent a file, and then we times 2 to the 12 because that is the size of each block. Okay, assuming this is also power 2 to the 12 to make it even simpler. Okay, so basically say, basically I'm saying this. Will you agree with me that DI size is roughly equal? I would say roughly equal because depending on you have some leftover, is roughly equal to DI blocks. Sorry, this should be Perl, is that right? And then times the block size, which in this case is 2 to the 12. Will you agree with me, this two number? This is the third line.
Yeah.
Okay. Okay, I want to tell you that answer is wrong. Then I want to tell you there are three possible relationships between these two. One is they're equal. One is they're greater than, means the DI size is greater than DI blocks times block size. The other one is a smaller and equal. Which one of the three is actually the correct answer? The relationship between these two. It's a tricky question. What? Sorry?
Less than or equal to.
Less than or equal? Okay. The thing is that I'm actually going to show you an example. In fact, the answer to this is very tricky because all three are possible. In fact, I'm going to show you an example, which is actually DI size is much, much greater than DI blocks times block size. Because this is actually, I'm going to introduce a concept between what we call logical file size, versus physical file size. Okay, so logical file size means that it's your data file, your size of the file. Whatever file you create for a movie, for a document, that's logical file size. But physical file size, number one, you should know that physical file size is basically say how many disk block I need to allocate in order to support this file. So it's not just the data block, but also the inode block, also the indirection block, the pointer block, they all count as the DI block. So that's number one you should know. Okay, so there is a two issue. Gradually, you will be surprised what sometimes the logical file and the physical file could be dramatically different. Okay, so having said that, I'm going to show you a piece of program. Let me see if this time I can actually make it bigger. Okay, I assume you know C. Okay, this is a C program. I wanted to spend a few seconds to just take a look at the program. You know what I like to do? I like to split all the students into different groups. I want you to just quickly discuss among yourself to determine what this program is doing And basically it created a file called sss.txt. And what is that file looks like? Okay, I want you to focus on what is this file looks like. All right, so let me do a breakout room very quickly. Just wait, I cannot do that because if I put you on breakout room, you cannot see the program. Okay, forget it. Just don't go to breakout room. For you to just take a look at this program and tell me what you think this program is doing. Or if you have any question about you don't understand part of the program, just let me know. So any volunteer from this class can share with all of us about what's your understanding about what this program is doing.
I think it is seeking a random location in the file and then writing 4 random bytes at that particular location.
For 1,000 times, right? That's correct. That's exactly correct. So okay, we find 1,000 different location and then store those things there. Okay, good question. Good observation. The follow-up question is that how many disk block do you think I actually need to have to support this file? Roughly, how many disk block?
It would just need 1,000 times how many ever bytes it's writing, but
Right.
the file size would be much larger.
Right. Exactly. You're right. That we need definitely we need about 1,000 block to represent those 1,000 random location. And also we probably need some indirection block, the what we call pointer block to actually be able to pointing to the logical location of this file. That's pretty much every blocks I need to represent this file. But just to let you know that this program, by the way, when I run this program, you will see the screenshot. It's based on the 32-bit architecture. And the file size of this file, logical file size is 2 GB. But the thing is that the number of disk block that's required is much smaller. So essentially, the file sss.txt is a file that's actually contain a lot of hole. So it's logically it's a big file, but there is a lot of hole. There's nothing. And then occasionally in those 1,000 locations, you have some content, but that's it. And that's basically this program. So let me actually show you some of the program that you can see what's actually executing. So I'm actually running this program. So you can see that before I run this program, the directory is, oh, it's been cut off. Let me see. If I do this, yeah, wow, it's get cut off. That's interesting. This is a new version of the Microsoft. Anyway, so you can see that before I run this program, the disk usage using this command called du is essentially only 10. Means that I'm using about 10 block in this directory and with this executable with this program. So I haven't started running. Okay, so now I'm actually running this program. I run this .t, and then you can see that if I do a ls-l, the sss.txt, if you do ls-l, which means that it's a logical file size, it says it's about 2.1 GB. It's about 2.1 GB. But if you actually use disk usage of the same directory, now is about 17,000 blocks. By the way, this architecture, each disk block is 1 KB. So can someone tell me that how big the memory, the disk usage with 17,000 bytes in this case?
17 megabytes.
Exactly. So essentially, I'm actually only used about at most 17 megabytes of disk space. I actually represent a file size of 2.1 gigabyte. So that's the difference between logical file size and physical file size. So logical file size is much, much bigger in this case compared to the physical disk usage. That is why I go back to this code to actually show you the difference between these two. Okay, so this two is one is DI size, one is DI block. So DI block is just physically how many bytes. In this case, DI block is going to be 17,000, but the DI size is going to be 2.1 gigabyte. Okay, just to let you know, I mean, the concept about this is not just about how do I keep tracking the information, but in file system, this becomes really interesting when you will be able to touching on some file which you don't even have it. So for example, I could potentially access a file which is much larger, but I only have with the USF2 design, I actually only access, or I only own a small portion of that file. But in terms of the application program, they can just still access the file based on whatever information I need to do that. Okay, so that's the difference. I want you to learn about the difference between the DI size versus DI blocks, which is represent the logical and the physical. And one of the direct, so this is what we talk about, by the way. I probably should give you this example, which is, I think is interesting. Let me actually, where is my, okay, here. So this is what we're talking about. The gray area represent the whole file. Logically, the file is huge, but physically only a few blocks that's actually have a content. So that's the orange represent the physical perspective of the file, where in the context of a logical file, which is the gray area, everything. Okay, so that's, and one of the immediate application you have is actually like a BitTorrent. So for example, sorry, I should actually ask the question. Any of you have ever used BitTorrent?
Yes, I have.
Okay, so okay, that's great. Yeah, so what BitTorrent is doing is that you actually have an empty file that this is a movie about 4 gigabyte or 8 gigabyte movie. And the thing is that you actually gradually sharing what we call piece with other user. So essentially, none of us actually own the whole movie except maybe one or two, which we call seed, that has the complete movie. But the movie got gradually distributed physically, with everybody has a logical over here. Okay, so the thing is that usually when you have a BitTorrent, for those of you who have been using BitTorrent before, you probably realize the following is that you actually have to wait until the whole movie was downloaded 100%. And then you start to use the application like a QuickTime to actually start to play the movie. Okay, that's a typical way of people are looking at BitTorrent, is that because I have that, I can do that. But back when BitTorrent was actually used extensively, we actually discovered, if you understand the concept of physical file and the logical file, you can actually start to view the content of a movie or any kind of application when you're only a small portion of the content are being downloaded. For example, in this case, I'm only download this 5 pieces of the whole movie. The thing is that your application can actually, the quick timer can already start to actually be able to look at this movie. If you actually know the position that this particular portion is available, you can actually directly move the position over here and start to interpret this one. Okay, so this logical side of physical side of concept actually sometimes help us to develop a different kind of coordination about file sharing, and also the application need to access to that. And the one of the undergraduate project, which is when I taught ecs251, I asked them to do the following. Let me see, do I have that? Yeah, I do have this here. So remember my first lecture, I said the operating system sometimes need to coordinate the application, different application, they need to coordinate to do something. So one of my final project for undergraduate operating system is for them to actually be able to coordinate 2 applications. One is the BitTorrent client, one is the player, like a quick view this picture. So what happened is that whenever the player is trying to watch the movie, because when you fast forward to a particular logical position of your file, when you actually move over there, the operating system kernel will receive a offset that you want to access this particular portion of the file. And instead of trying to open the file and then fail, because that particular portion of the file hasn't been downloaded yet. So instead of just simply fail to tell the player that, sorry, the file doesn't exist, it will redirect that position to the BitTorrent client. So essentially, the information for the player got passed to the BitTorrent client, and the BitTorrent client will put a higher priority to grab that piece. So essentially, you are going to have some extra delay because the BitTorrent client is actually prioritize their grabbing the pieces, and then they will grab the pieces as you actually move along your player. So in this way, we can actually provide a new function into the operating system to let operating serve multiple coordinating applications at the same time. Okay, so just to let you know that this is an excellent example. Even today, the commodity operating system kernel hasn't been able to do that. Okay. Okay, any question? So I hopefully, let me see. Okay. Yeah, hopefully you kind of have understanding about the I know, and also with the I know you can actually, by the way, there is a one property about the I know. Now I remember something I forgot to mention. It is because of the structure of I know, it's actually possible for you to represent a logical file like the way I actually represent just a couple minutes ago. So that's another very nice property about the I know architecture, I know design. Okay, let me go back. I think there's lots of questions on the chat I should handle first. Let me take a look at this. Wow, there's a lots of questions. Let me actually go here. Oh, I see. Okay, okay, that's a great idea. I should probably convert it to PDF. Oh, it's just rendered. The sleep time is 100 seconds. I would just writing program looks like that. There's no particular good reason. Okay. Okay. If you look at the file, those file, that's interesting. That's an excellent question, Dolores. The question is saying that, well, where is the hole? The thing is that we need to think about the file as a I know. So essentially, the file is really I know. So when we think about any file, it's really I know. So for those files which they don't have the entry, let's actually make an example. I know this is a perfect slide for me to talk about. Assuming this file only have this 5 block that has content, assuming those gray represent is those blocks of file that's actually have content. The rest are all empty in sss.txt. In other words, what I'm saying is that from my perspective, when I look at the I know, this is the only block that will exist. This I know block will always exist. This block will exist because it has a gray block. This block will exist on the hard disk because it has 2 of the block that actually has block. And this block will exist, but none of the other double indirection block in this level, because in this level, remember, we have 512. Only those 2 blocks out of this 512 block will exist. The other block, they will not exist. It means that all the pointer here will just be null. And the thing is that similar for triple indirection, essentially all the data block that's actually empty in SSSX, number 1, they will have no representation as a data block. Number 2, all the indirection block is not pointing to those 1000 whatever block that has a physical content will not exist. So this actually is a very efficient representation. I use a minimal amount of memory, disk space to represent that file with a lot of hole. Did I answer your question, Dolores? Okay. Yes, that's correct. That's correct, Xiao. That's correct. Okay. Let me see how I'm doing here. Let me actually stop sharing. And I want to end the program. I have about 16 minutes. I think this is a good place for me to move to do something else, okay? I won't be able to do like a directory block, Duran, because that will be next Tuesday, and also some topic. But I want to tell you some of the questions typically related to the a typical example to what I just shared with you. So there was a few, oh, I haven't shared my screen. I forgot to do that. Sorry about that. So these are the typical questions we can ask. For example, how many disk blocks can a file system have? And how many level of IO indirection will be necessary to store a file with 2 GB? And what's this one is actually pretty tricky. What is the largest possible file size in I know? And also, what is the size of I know itself with of a 10 GB with only 512 megabyte downloaded? So in the slides, I actually give you an answer. You can see that the answer could be fairly complicated, especially the third one. There are actually 3 possible answers. The smallest one should be the large possible file size, but we'll talk about that later. But I'm going to stop here, and I'm going to turn to something a little bit different. Oh, I should actually give you this slide to just let you know what's the file size looks like. Yeah, this is the slides I want to tell you. This is a typical the hard disk configuration. You can see that this is your hard disk. The first, you have a hard disk, you separate the hard disk into different partitions. And for each of the partition, you're going to configure them into a file system. So this is the file system. And the file system has the following block. Oh, I forgot actually one block. The first block is called boot block. If you want this to be bootable partition, then you need to contain the information about the booting sequence and things like that. It's the boot block is the first one. And the second block is called super block. And after the super block, you have a region of the hard disk is allocate to inode. So though every single thing here is called inode block. And then the rest of the block over here are actually basically either directory block, data block, or indirection block. The indirection block is also here as well. Okay, so that's the just give you a high level view about on your hard disk, what kind of disk block that you will have. Okay. Okay, before I actually want to talk about some of the exam question, I want to actually start to give you some feeling about what my, in fact, what I'm going to do is I'm going to share with you all my previous final exam and midterm exam. So you get a feeling about how to prepare for those, because after I'm done with this part, I'm going to give you a midterm, the first midterm exam. So any question before I actually go to that part of this course?
Professor, when you say the size of inodes, does it count the size of indirection blocks as well that sits on the actual data blocks?
No, the size of the inode is only count the 256 byte with UFS2 inode. So that's the basic inode information, but it doesn't count the what you call indirection block, because the pointer block or indirection block, they could be many. It's actually harder to count depending on the size of the file, depending on whether you have a file with whole, like a logical file, physical file size difference, that the amount of the inode disk block is actually hard to estimate case by case. But the basic inode, which is that 256 byte, that's always fixed. Does that answer your question?
Yeah, yes, Professor. So in the inode data structure, there's a, as you said, there's a di underscore blocks. Does that counter also store the number of indirection blocks as well, or just the data blocks?
It actually counts everything. It counts data block. It counts the indirection block as well. Yes, it counts every disk usage for this particular file.
Thank you.
You're welcome. Yeah, go ahead. Go ahead.
Topic, but I was interested on how the data recovery tools work. If for example, I want to recover a file, there are several data recovery tools. Even if the file is deleted from the file system, they search for the particular file and then they retrieve it.
Mm-hmm.
So I was interested how they retrieve the inode information, even if the inode is deleted from the file system.
Right. Okay. That's a great question. Okay. So I like to spend some time about those tools, how that will work. Okay. Now I keep getting this file. This one. Okay. That's a great question. I will. In fact, I don't have a slide, so I'm going to make a slide. Okay. So how do I actually recover an inode, right? Recover a file. So the thing is that, remember that if it's inode block, let's actually talk about inode block. So inode block is this block, so is assuming it's a 4K byte, right? 2 to the 12. And this block will contain, as I said, is about how many? 256, is that right? 256 inode in a single inode block, right?
I think it was 16 inode blocks in a single block.
Are you sure? Because each block is 2 to the 12, right? And each inode is 2 to the, oh, you're right. Yeah. You're right, sorry. Each inode is 256 bytes. So yes, you are absolutely right. Thank you. 16, not 15, 16. So it's equal to 2 to the 4. So we have 16 inode over there in a single inode block. Remember, this is in your hard disk. When you remove a file, okay, later, I haven't talked about directory. When you remove file, it's not really about removing the inode. It's about removing in the directory. So later, when we talk about directory, you will see that when you remove a file, you essentially just remove two things. You remove the entry that to the inode from the directory, and such that you no longer can actually find this file. The second thing is that, well, this particular inode in this inode block, this particular 256 byte, it will not be replaced until you actually create another new file that you need to use that disk space. I mean, the chances that if you have not, your hard disk is not like 100% full, the probability that this 256 bytes are still there. So I'm saying that even though you remove the file within a short period of time, those 256 bytes are still there. What does that mean? It means that as long as I can find the older version of the directory block that actually still have the inode number corresponding to that file, then as long as I can start finding this inode, then I will be able to, from this inode, I will be able to access to every single data block or indirect block. Assuming this is always depending on whether the resources has been overwritten by the newer file activity. Does that make sense?
Yes, Professor. So as long as the inode information is intact, you say we can recover the data. So that makes sense.
Right.
But is it completely possible to retrieve the data if the inode information is overwritten?
Say it again. Sorry, the last part.
Yeah, sure. So is it completely impossible to retrieve the data if the inode information is overwritten? If the inode information is lost, can we still retrieve the data, or is it impossible to retrieve the data?
I think it's still possible. To be honest, everything is possible, because if inode is being removed, essentially what I lost 15 pointer, right? What inode has is those 15 pointer. If I actually lost that 15 pointer, it's really hard for me to reconstruct that 15 pointer, but it's not entirely impossible because as long as all my indirection block and those 15 pointer, if I can somehow use another way, I don't know how you can do that. Maybe you will do exponential number of combination and trying to actually see whether you can actually reconstruct the first 12 pointer by a lot of trying. That's possible. But I would say in a UFS2 operating system, file system, if you lost your inode, you pretty much really hard for you to actually access to that.
Thank you, Professor.
You're welcome. Yeah. By the way, the reason I say is always possible is because the hackers are really good. Just be honest with you. Some of the hackers are really good. They have all kind of way to actually be able to recover information that's being overwritten. So that's why sometimes to get rid of everything, sometimes we do what we call low-level disk format. If you do a low-level disk format, basically you wipe out every single memory cell in your hard disk to 0. That means you basically erase data block, indirection block, directory block, and also the inode block completely, then it's actually really hard for you to reconstruct your information. Okay, hopefully we don't need to worry about that. But anyway, okay. All right, thank you for the question. I have about 4 minutes. I just want to tell you that number one, I'm going to share with you my previous midterm. Let me actually see which one. This one, is this a midterm? Yeah, so this is the midterm. This is midterm actually talk about, you can see, oh, wait a minute, this is what we just talked about. This is the midterm I actually give. You see that what's the largest possible file size can represent inode with the file system. You see, this is exactly what we're talking about today, right? And the second question I asked is about a concept called, this is called soft update. This is the way that FreeBSD UFS2 maintain a reliability about to synchronize the information, the blocks from the memory and the hard disk. How do you actually, because think about that, we're retrieving information from hard disk to memory, but you're also going to write back the memory to the hard disk. And in the process, that suddenly you lost your power. And how do you actually maintain the consistency of your file system? That's actually very important. We want to make sure it's robust. And that's why it's important to have the soft update. If you look at the question, it's actually typically asks you, you have, this one is inode block. This is inode block, this is directory block. So essentially, how do you actually write back the inode block with the directory block? Which this part, if you don't have any clue, don't worry, you will know this very well. I assume in a week, you will know this very well. But I also want to tell you that the other type of question I typically ask the student, this one is kind of a bit freestyle. By the way, all my final exam is going to be open book. So open book, open internet. So you can actually retrieve any information you want anytime. You cannot communicate with another person, but you can communicate with another information using Google, whatever. So the thing is that I even don't know how I'm going to run the midterm exam, to be honest, because it's still unclear until now whether we will have in-person lecturing next Tuesday. But just to let you know, regardless what will happen, I will actually keep recording, keep using Zoom. So at least for some of us who cannot participate in person, that they can still participate over Zoom, live streaming, okay? So for example, this is an exam question I really like. I think this exam I gave in 2016. I'm actually talking about a system service called Appreciation. It's actually grabbing the information from AIoT sensor and try to automatically determine what need to be sent to encourage another person. It touched a lot of issues, so it's kind of really, really freestyle. You probably, I'm surprised, by the way, I already posted this. This is already like 5 years ago until today that we still don't have such kind of service, even though we see that AIoT is getting more and more popular this day. Essentially, this is actually a huge issue about how do you design a system, including operating system kernel, to protect the information and to discover the information that's necessary to enable application to coordinate with each other. Okay, so I'm going to post this to you, so just you have some feeling. My plan today is having some part of midterm is directly related to the lecture, but some part of midterm is like this kind of scenario, is ask you to think without boundary about what can be done today. But this one, it was actually the final, not the midterm. So the good news is you probably won't see this in the final exam because we don't have a final exam. But some of the idea will be matriculate into your final project, which I will discuss with you later. Okay. All right. I think my time is up. Any other question? Okay.
Yeah, Professor, I had a question. In the program that we executed that generated the sss.txt, its logical size was 2.1 GB and its disk usage, or the number of blocks it needed, translated to a size of 170 MB.
Right.
So if I have a free hard disk space of 16 GB, after I execute the program, what should I see? Am I left with 13.9 GB free space, or am I left with 15.83 GB of free space?
If you use disk usage or DF, which is the disk file system, it will actually show with 16 GB minus 17 MB.
Okay.
So essentially, it's possible. By the way, okay, thank you for asking this question. I should say that different file system will handle the following situation differently. Windows file system, if you create a virtual file, logical files like that, it will reserve the whole space for that file. Means that if your file have a hole, that even those hole, I will reserve the space. So the disk usage will be dropped down, like you said, 2 GB. But in UFS2, which is the file system that FreeBSD use, you could potentially, the logical file size of a bunch of file add together much, much larger than your physical hard disk space. Do you understand what I'm saying? So depending on the file system, some of the file system is like a FreeBSD. It allows you to do this kind of very small amount of hard disk usage, and they can actually support logically much bigger file size. And later we'll see that this becomes even more interesting when we look at Google file system. So in Google file system, GFS or Hadoop, it becomes logical. Is actually doesn't matter. The logical is all outside in the internet and cloud environment, where you only have what we call the master index node, which is actually contain pointer to different chunk or pieces around the internet. And over there is definitely more in line with what UFS2 is designed to operate.
Okay, thank you.
You're welcome. Okay, so thank you very much. You all have a good weekend. Let me actually take a look the question. I have a few questions. Okay, I will announce the date for it's probably going to be the beginning of the 4th week. Okay, today is the end of 1st week, so it will be about 3 weeks from today. And the midterm is not going to be take home. The midterm is going to be either, so I don't know actually. I don't want to be take home because that will be too much time for all of us. It will be either in person or we actually all log into the Zoom, and then you actually we all give everybody 2 hours and we work on that, okay? Okay, Tom, I just want to let you know that yes, you can either join the class next week, Zoom or in person, if in person is become available, okay? Oh, okay, remote instruction will continue. Oh, thank you, Charlie. I haven't checked my email for a while. Okay. Okay, 3 more weeks. Okay, that sounds good. Okay, I mean, in any case, I'm going to provide the online streaming. My plan is provide online streaming until the end of the quarter. Okay, it doesn't matter whether they do a January 28 because So just let you know what I'm doing online streaming. The way I do online streaming is that I actually go to the classroom. When the campus is open, I'm going to the classroom. I'm actually facing all the students in front of me who want to participate in person, who has test negative and also wear mouse mask. And then I'm actually going to open my Zoom and then basically do exactly the same as I'm doing. So for those of you who cannot participate in person, you can actually go to the Zoom. You will be in sync with the rest of the students who are in the classroom. Okay, so just to let you know. All right, so you have a good weekend, and so happy to see all of you here. I think I will have office hour in, I forgot, 4 o'clock, 4:30, I forgot, later. Okay, so if you want to join, the same link, okay, to join my office hour. All right, talk to you later. Bye.